first speaker today is NASA astronaut and International Space Station mission specialist Donald Pettit. Dr. Pettit holds a bachelor's degree in chemical engineering from Oregon State University and a doctorate in chemical engineering from the University of Arizona. Since August of 1996, when he first reported to Johnson Space Center to begin astronaut training, he has logged more than 370 days in space and 13 EVA or spacewalk hours. He was a crew member of STS-126 and has lived aboard the International Space Station for 5.5 months during Expedition 6, and again for 6.5 months as part of the Expedition 3031 crew.
I'm Don Pettit. I was fortunate enough to be a crew member during Expedition 30, Expedition 31 to the International Space Station. And during that time, I had the opportunity, the good fortune again, to work on the BCAT experiment. And I was working with the PI on this, directly talking to him on the ground. This was Matt Lynch. And he had a series of these ampules filled with a colloidal suspension, and he was expecting to get ripening in these colloidal suspensions like he'd seen in similar makeups in the past. And these suspensions, after sitting for many weeks, still appeared to be water clear suspensions. There wasn't any significant structure occurring in these ampules. And this was when you would look at them with white light, and the pictures that were being taken with this automatic camera that was set up both had transmission and reflective views, and it looked like nothing really was happening in these ampules. And we were going back and forth just like two scientists do in a laboratory, except we were abstract from each other, but it was almost as if Matt was there with me. And we were wondering, well, what happens if we poke it with a stick? Or what happens if we shine light on it this way? Or what happens if we do this? And because we were baffled by why we weren't able to see the kind of structures that were expected. And I happened to have one of these 5 milliwatt green laser pointers, and I thought, let's shine this laser pointer through the sample. And when I started to shine this laser through the sample, we could start to see structure that was there. This was structure that had too low a contrast in terms of its light scattering to be seen with white light, but through the intense columnated beam of the laser, we were able to see that there were scattering centers in this ampule, and that ampules that had been freshly stirred did not seem to have these scattering centers. And again, this was an example of Matt and I working together, again, sort of with the naivety of two little kids working on a science fair project, not really knowing what was going to happen, and just wondering, well, let's try this. Oh, that didn't work. Well, let's try that. Well, that didn't work. Well, let's try it this way. And then, wow, we're seeing something.
While in microgravity, Dr. Pettit has observed colloids and biological samples under different influences and circumstances.
When you're in a weightless environment, you can look at the process of ripening, you can look at the process of flocculation, where these larger particles now will not settle out because they remain suspended in the system. It's really good from a crew member's point of view to be working directly with the PI, and that seems to be the general trend right now in payload experimental science, is to be able to actually talk with a PI. Have a PI, designs an experiment, knows what they want, but sometimes things don't work out quite as planned when you get on orbit. Sometimes other things happen, other phenomenology may be visible, and that's where it's nice to have a human in the loop on the orbiting platform, so that working with the PI, you can make new observations and possibly change the experiment real time and collect data that if it was all canned, pre-programmed, you might have missed.
Among Dr. Pettit's many accomplishments is the invention of an on-orbit coffee cup.
Oh, the coffee cup. This is an example of using contact angle, wetting properties, using these properties to make an open container of fluid that you can move around and drink from in a weightless environment, not unlike being on the surface of Earth. And this basically came about that we suck all our fluids through a straw from a bag on orbit, and this is a perfectly fine engineering solution to how do you drink your beverages in a weightless environment, but it's a little bit on the gauche side. And being human beings, you like the idea, particularly on occasion, to be able to drink your beverages from an open container like we do on Earth. I got this idea of using some plastic sheeting from our orbital data file, and I taped it up in a particular shape where it had an acute angle using Kapton tape. And with this shape, it was able to control the free surface and allow it to creep up the side, to basically channel flow and park itself near the lip of the container. And then this allowed you to not only move the open container around without sloshing the fluid out, but it allowed you to drink the fluid from the container because of this acute angle. This is based on a paper written in 1969 by Conkus and Finn that talked about a channel flow if you had an angle that was less than the quantity 2 times 90 minus the wetting angle. So this was just an example of being able to apply all this surface chemistry that I learned in college and apply it to something somewhat whimsical, an open cup that now allows you to drink in a civilized manner in an orbital environment.